In this lecture, we're going to start talking about common distributions. So this is going to kind of dominate the next two lectures. And basically, we've now learned a bunch of different features of random variables and ways of kind of understanding random variables. We looked at CDFs, PMFs, PDFs, MGFs, expectation, variance, moments, and we've looked at some examples, but we're basically going to spend the next two lectures looking at a lot of examples. And we're going to kind of go through some of the common distributions that one would see in probability. This won't be exhaustive, it's not going to cover everything, but it'll give you a good sense of kind of the range of various distributions, give a bunch of examples of common distributions here. So some of these we've talked about a little bit, and we're going to start today by talking about the discrete uniform distribution. So in some ways, this is one of the simpler discrete distributions. Our notation here, we would say that a random variable x is distributed as uniform. And to start, we're going to just consider uniform over the numbers 1 to n. So what we mean when we say x has a discrete uniform distribution over the numbers 1 to n is that the PMF is equal for all values 1 to n. So this is a discrete distribution, as the name implies. And if we look at a graph of the PMF, fx against x, it would look something like this. Our support is the numbers 1, 2, 3, all the way up to n. And at each of these values, we'll take on the value of 1 over n. Okay, so our kind of picture of our PMF, our stick diagram, looks like this. And so we could write this out as the PMF fx is 1 over n for x is 1, 2, 3, all the way up to n. And it's kind of implied by this that it's 0 everywhere else. Note that we can check. So let's just put a box around that fact. It's an important fact. We can check that. Of course, for this to be a valid PMF, it better be positive, and it better sum to 1, right? So if I look at the sum, I goes, the sum over my support, that is I goes 1 to n of my PMF, f of I, that is just sum 1 to n of 1 over n, which is n times 1 over n, which is 1, right? Clearly this PMF is positive, it sums to 1, and so it's a valid PMF. So let's just say PMF. Okay. The next thing we could look at is we could look at what the CDF is for this thing. So what's the CDF for a discrete uniform distribution? Well, the CDF is going to be, typically we denote it as capital F of x. And for this discrete distribution, it's the sum of I less than or equal to the lex of the PMF, right? That's a relationship we know for discrete random variables between the PMF and CDF. And it's probably most useful to draw a graph here of this. So let's draw a little graph of my CDF fx against x. And so let's see, if I choose a value, say less than 1, my PMF is 0 for all these values. So up into, so let's just actually denote my support here, right? Up until 1, my CDF is going to be 0, right? It's going to be 0 because there's no probability I'm ever less than a value. Up until I hit 1, at 1, the probability I'm less than or equal to 1 is 1 over n. So it will jump up here to 1 over n. Between 1 and 2, the probability, say, I'm less than or equal to 1.5, it's the same thing as the probability I'm less than or equal to 1, which is the probability I'm equal to 1. So that will just be constant all the way up until I hit the next value of my support. And I know the jump in my CDF has to be equal to the PMF at that point. And the PMF, of course, is 1 over n, so I jump up to 2 over n. And this will be flat again up to 3, and then we make another jump up to 3 over n, etc., all the way until eventually we will get up to the number 1, somewhere up here, when eventually I get up to n, I will jump to 1, and it will be 1 henceforth, right? So let's just move this CDF a little bit. We could write this in a couple of ways. One is you could write it as kind of a piecewise. It's 0 if I is less than, I'm sorry, here we're using x. If x is less than 1, it's 1 over n. If we're between 1 but less than, bigger than or equal to 1 but less than 2, it's 2 over n. If we're bigger than or equal to 2 but less than 3, and so forth, all the way up to when we get to n, it's just, I'm sorry, when we get to x being bigger than or equal to n, it's just going to be 1. A compact way of writing this is, well, let's write it this way. It is the floor function of x over n for, let's say, x between 0 and n, and it's 0 if x is less than 0 and 1 if x is bigger than 1. So the floor function just means round down, and that gives us the step function. That's really the floor function. So we can put this in the box. That's the CDF. I think we've talked about this a bit before, but that's the CDF of this discrete uniform distribution. And it's a valid CDF. You can check, for example, all the facts that need to be true for it to be a valid PDF. For example, it's non-decreasing, which we can see from our graph. It is right continuous, which we can see. It's kind of the step function. And the third thing that needs to be true is that the limit as x goes to infinity is 1, and the limit as x goes to negative infinity is 0. And both of those things are true. It's only 1 at infinity and 0 at negative infinity. So you can check those things, you can convince yourself that they're true. Other things we can talk about for distributions now, we can talk about expectation, what the expected value of the distribution is. So here's something we haven't seen before. What is the expected value of x if x is a discrete uniform distribution? And of course, we have a formula. This is the sum, and I can just sum over my support. My support is I goes 1 to n. And in this case, it's I times f of I. Alternatively, you could write it with x. Let's just use I in this case. And so this is I goes 1 to n, I times, and what is f of I? F of I is just 1 over n for all of those values in my support. And so this is 1 over n times the sum of the integers between 1 and n, right? And there's a formula for this. I'm not going to derive the formula, but it's a formula that you can look up. And I wouldn't expect you particularly to memorize it, but the sum of the integers from 1 to n is n times n plus 1 over 2. So this is a formula. Let's just say known formula. And so that gives us a final answer of n plus 1 over 2, right? And this was our expectation. So expected value of a discrete uniform on the numbers 1 to n is n plus 1 over 2. That is basically the midpoint here, n plus 1 over 2. So my balancing point is midpoint, n plus 1 over 2. It's the average, the arithmetic average of 1 and n. And add n and 1 divided by 2, that's kind of average. And that makes sense. We have, whoops, I should probably draw this not for the CDF. Let's redraw this for the PMF. So my balancing point here, balance at n plus 1 over 2. All right, and that makes sense because my probability mass is uniform on all these values, and so if I were to try to balance out these masses, I would just put it directly in the middle of them, the arithmetic average of them. So that's expected value. Of course, we could also ask for variance. And so to calculate the variance, we could instead calculate the second moment of this thing, expected value of x squared. And we know if we know the first two moments, we can get the variance. And so again, I'll kind of skip some steps here, but what we're going to get if we ask for the second moment, it's going to be the sum goes 1 to n of now I squared times 1 over n. And that, again, factor out that 1 over n, it's the sum from 1 over n of the squares. And there is, again, a known formula for the sum of the squares from 1 to n, which I'm not going to expect you to know. And that formula is, well, so first we have our 1 over n out front, and then the sum of the squares is n by n plus 1 by 2n plus 1, all that divided by 6. And so this, we can cancel at these ends, should just give us n plus 1 times 2n plus 1 over 6. Okay, so that's the second moment, expected value of the square. Of course, if we want the variance here, I have my shortcut formula that says the variance is the second moment minus the square of the first moment. Expected value of x squared minus the expected value of x quantity squared. And I've now calculated both of these things, right? So it's n plus 1 by 2n plus 1 over 6. And then I subtract off my mean, n plus 1 over 2. Of course, that's quantity squared. And I'm going to say algebra. I'm not going to do out the algebra. This can be simplified to n squared minus 1 over 12. And I think you can believe that. 6 and 2 will give us a denominator of 12. And the top there is going to simplify to n squared minus 1. So that is my variance, right? Again, that is my variance here of x. So for my discrete uniform distribution. What else can we do? We could talk about the moment generating function. That is the MGF, which was kind of the main topic of the previous lecture. And so we could ask what m of t is, what's the moment generating function for a discrete uniform. And of course, we know for any random variable, it's the expected value of e to the tx. And in this case, the expected value is for sum I goes 1 to n, that's my support, e to the ti, and then I multiply by f of I, which of course is just 1 over n. And so I can factor out my 1 over n, and I'm left with the sum I goes 1 to n. And I'm going to write this as e to the t to the I. Okay, that's an okay thing to do by rules of algebra. And then we just need to simplify this a little bit more. We need to recall that what the partial sum of a geometric series is. So call back all the way to Calc 2. The sum of a geometric series, if we sum I goes 1 to n minus 1 of r to the I, this is kind of the partial sum of a geometric series. This is 1 minus r to the n over 1 minus r. All right, if I let n go to infinity, it just becomes 1 over 1 minus r. And this is true as long as absolute value of r is less than 1. And so we can kind of rewrite this moment generating function as a partial sum of geometric series. We just need to change my variable. I can instead say that this is the sum from 0 to n minus 1. So if I reduce the index by 1, then I need to increase it in the sum by 1. So that's an equivalent way of writing it. I go 0 to n minus 1 of e to the t to the I plus 1. And I could factor out one of those e to the t's, right? I could say this is e to the t over n. Sum I goes 0 to n minus 1, e to the t the I. And so if e to the t is r, and if as long as this thing is less than 1, then this is a partial geometric series, the kind of partial sum, and so we can simplify it according to the formula, kind of Calc 2 formula there, and it would be 1 minus r, which is e to the t, to the n, over 1 minus e to the t. And of course we could just simplify this a little bit more. This would be e to the t minus e to the t times n plus 1 over n 1 minus e to the t. So that is my moment generating function. This is true as long as e to the t is less than 1. E to the t is always positive. We don't really need absolute value bars, but if e to the t is bigger than 1, that partial sum might not work so well. But that's the MGF. And you could check that if I take derivatives of this and I plug in 0, I should get back my first 2 moments, which we calculated up here. Right? So this was a discrete uniform distribution on the numbers 1 to n here. Well, what about if we just have arbitrary starting and end point, a to b? So as kind of a twist to this, let's do kind of a little harder case where x, we're going to say, is uniform on the numbers a to b. Okay, so basically what that means is that my support is a plus 1, a plus 2, all the way up to, all the way up to b. And it has a equivalent, equal, or uniform probability mass at each of these points. So one question is, what is, so this is kind of f of x versus x. Question is kind of, what is f of x in this case? Well, how many points do we have? In total, we have b minus a plus 1 points in the support. And so if I sum fx, sure, let's say fi, doesn't really matter. If I sum over my support, I goes a to b, I better get 1. And if they're all equal, then this sum here is whatever the value of my PMF is. Let's say some constant c, right? So it's c times how many points I have, which is b minus a plus 1. And therefore, this value of c better be equal to 1 over b minus a plus 1, right? That is to say that f of x is 1 over b minus a plus 1 for x is equal to a plus 1, all the way up to b. So it's basically the similar kind of distribution, but we're just shifting it. Now, instead of going 1 to n, it's going a to b. And so if, let's say, if we had some random variable y that was distributed uniform 1 to n, then we could make a random variable x that was distributed a to b. We could make that from y by, let's see, we would take y and we would add a plus 1, and as long as n is b minus a plus 1. Okay, so if we had a random variable y that was distributed from 1 to b minus a plus 1, we could make a random variable x that is distributed uniformly between a and b by just taking y here and adding, whoops, not a plus b, we'd add a minus 1, right? Adding a minus 1. Subtract off, so it'd start at a 1 plus a minus 1, right? So it'd start at a, which is what we wanted. The second point would be a plus 1. The third point would be a plus 2, etc. When we got to n, it would be b minus a plus 1 plus a minus 1, which would be b. So in that case, this would be, if we looked at a uniform on 1 to b minus a plus 1, and we added a plus a minus 1 to it, we would get a uniform a to b. So let me just write that. And x uniform a to b. So it's basically just kind of shifting a shift of our other uniform, right? The reason I did it this way is deriving the facts for the discrete uniform on 1 to n is actually pretty straightforward. And then we can just use some of our rules to re-derive facts for the general case on a to b, right? So, for example, so what did we calculate up here? We've already looked at what the PMF would be. The CDF is not super interesting, but we can look at expected value, variance, moment generating function, right? So, as we said, the PMF is still kind of 1 over n. But in this case, n is b minus a plus 1. Okay, so that's similar. What about the expected value? We could look at expected value of x, let's say, and the expected value of x would be the expected value of y plus a minus 1, where y is uniform on 1 to n. And we know by our rules this is just expected value of y plus a minus 1. And expected value of y, we said was n plus 1 over 2. So we can plug that in. Oops, sorry, a minus 1. And n in this case, we're saying n in this case was b minus a plus 1, another plus 1, over 2 plus a minus 1. And so if we simplify here, what do we get? Let's just write it this way. B minus a plus 2 plus 2a minus 2 all over 2, which is b plus a over 2, or a plus b over 2. It is the arithmetic mean of a and b. So in the case where we have uniform over the numbers a to b, again, the balancing point, the mean, is just a plus b over 2. It's the in-between point between a and b. That makes sense. This was similar to how in the case where it's uniform 1 to n, it was n plus 1 over 2, the middle point. And so what we've seen here is that we can often derive, if we had brute force tried to derive this expectation, it would have been much more of a hairy kind of calculation to do. But what we've done is we've solved it first in a simple case on the uniform 1 to n, and then we use our rules about how we can transform things, say, what happens to expectation when I add a plus 1 to it. And that allows us to derive the expected value of something more complicated, some more general version of it. We can play the same game with variance. So if I wanted to know the variance of a kind of general discrete uniform distribution between some values a and b, again, this is going to be the variance of y plus a minus 1. But my variance rules say I can ignore additive shifts. So actually my variance doesn't change. We knew that in the case where if y were discrete uniform 1 to n, it has a variance of n squared minus 1 over 12. And in this case, we had said that n is b minus a plus 1. So what you get is b minus a plus 1 squared minus 1 over 12. And that's my variance, kind of my general case where it's between a and b. And you could similarly generate the MGF and for x, so mx of t. Last time at the kind of end we had a theorem that said this would be the moment generating function of y evaluated at a minus 1 times t, right? The general theorem was that if y were, let's write it this way, the general formula was that if I looked at the moment generating function of ax plus b, this was e to the tb moment generating function of x at at. And in this case, our linear transformation is just to add a minus 1. And so we just now evaluate the moment generating function of y, which we derived above, at a minus 1t, right? So MGF of y had what form? Well, this was our MGF of what we're calling y, which is discrete uniform over 1 to n, e to the t minus e to the t to the n, and that's e to the t times n plus 1 over that whole thing, right? So e to the t, except now we're evaluating at at, right? So it's e to the, or a minus 1t, minus e to the a minus 1t times n plus 1, and n 1 minus e to the t, and then we also, yeah, I think that's correct. And anything else we need to, no, that's incorrect, right? Let's go back here, right? And this is not correct. This is e to the correct way to apply this, right? So in our case, b is 0. No, this formula is not helping us here, right? In our case, let's just rewrite this out here, right? In our case, what we have is y, a random variable y, is, other way around. Random variable x is y plus a minus 1, right? Our formula says that m of x should be e to the a minus 1t times m y of t, right? There's no multiplicative factor, so that doesn't show up in our formula. All we have is additive shift, and the formula says that additive shifts end up out front in e to the whatever, right? So this is the correct formula. And so we get e to the a minus 1t, and then we plug in what we had derived above for the MGF, which is e to the t minus e to the t times n plus 1 over n times 1 minus e to the t. Okay. So it's a little confusing because our formula last time switched a and b. That's all that's happening. But in this case, now we can just kind of multiply through, and what we'll get is e to the at minus e to the we'll get t, and then we'll get n plus 1 minus 1 plus a over n times 1 minus e to the t. Okay? And let's do like 1 or 2 more steps. N, we said, was b minus a plus 1 plus a, and then it was b minus a plus 1 in the basement, and then it's 1 minus e to the t. So one more step will get us there. E to the at minus e to the t times b plus 1, because these a's cancel. And in the basement, we have b minus a plus 1 times 1 minus e to the t. And that is the general form for the MGF of a discrete uniform. And if you don't mess up like I did, it actually is quite much more straightforward than trying to derive that generally with all these a's and b's running around. So what we did is we derived it originally in the case of kind of discrete uniform 1 to n, and then we apply our theorem to get the general case on a to b. That's actually kind of a nicer way of doing it. Okay, so that's the discrete uniform. Let's now look at its continuous counterpart, continuous uniform. And so we'd say x distributed as uniform, and we'll just say in some interval a to b. So another way of saying this is x is uniform over a to b. And it means that what this means is that the density, is uniform over this interval a to b. So what my PDF will look like, right? It's continuous, so it's a PDF. What my PDF will look like, if I look at fx against x, is that over a to b, it's going to be flat. It's uniform. And it's going to be 0 outside of it. So that's what my PDF is going to look like. You can kind of draw dotted lines here if you want. And so there's going to be some value c where my PDF fx is going to be c in this interval a to b and 0 elsewhere. How do we know what value of c it should be? Well, we know fx or f must satisfy that if I integrate this thing over the whole real line, that better be 1. And so that constraint, that's supposed to read must satisfy, that constraint is going to tell us what c has to be, because the integral, of course we only need to integrate between a and b, 0 elsewhere, some value c dx, that has to be equal to 1, and this of course is going to be equal to c times b minus a, and so c must be 1 over b minus a. What this means is that if I look at the PDF for my discrete uniform, is that f of x is 1 over b minus a for x in a to b, and 0 everywhere else. So another way of thinking about it is that there's some area under here, and this area better be equal to 1. And this area is equal to, of course, the length here, which is b minus a, times whatever my height is, which is, we're calling c, and so c has to be 1 over b minus a. All right, in order for the whole thing, the area there to be 1, that's how it has to work out. And, saying that the PDF has to integrate to 1 is the same thing as saying the area under the PDF has to be 1. It's the same kind of thing as saying the probabilities have to sum to 1, but it's a kind of continuous version. Okay, so that's the PDF. Not too interesting. It's uniform at the correct value, so the whole thing integrates to 1. And that's why we call it the uniform distribution. We can look at the CDF for this thing. Now, for continuous random variables, the CDF, fx, is the integral negative infinity to x, and let's say of ft dt. Let's use another variable so we don't confuse x's. And let's, just for now, let's look at where x is between a and b. It's going to be easy when it's outside a and b. If x is between a and b, then this is the integral from a to whatever x is of, well, f of t, we know what f of t is. It's 1 over b minus a in this whole area. And we integrate that with respect to b dt, and that gives us, well, we can pull out the b minus a, and that will give us what? X minus a. So at least when x is between a and b, our CDF is x minus a over b minus a. A nice way of thinking about it is that, again, if I draw here my PDF, right? So here's a, here's b, it's uniform, and its height is 1 over b minus a. If I look at my CDF says if I have some value little x here, my CDF is a probability I'm less than or equal to this little x, which in this case is just going to be integrating this whole PDF over this area, or it's going to be that shaded region. And so on one side, its length of this box is x minus a, and on this other side, it's 1 over b minus a. And so the size of the box is the product, x over a minus b over b minus a. Notice that when x is a, that is, we're all the way over here, it's 0. And when x is b, we're all the way over here, it's 1. So we could draw a graph, kind of corresponding graph, let's say, of the CDF, and between a and b. It is linear. This is just a linear function, right? It's has a slope of 1 over b minus a and an intercept of, well, it has an intercept so that we're 0 here, and at b we are at 1, and has a slope of equals 1 over b minus a. When we're above b or below a, so when we're above b, caps out at 1, probability that we're less than or equal to some value bigger than b, it's always 1. We're always less than or equal to this value. And similarly, the probability we're ever smaller than a is 0. We're uniform between 0 between a and b. We're never less than a. So you get this kind of piecewise thing, and I suppose you could write it out in a full form as a piecewise function. It's 0 if x is less than a, it's 1 if x is bigger than b, and it's x minus a over b minus a if x is between a and b. Now, you've noticed I'm very sloppy with my less than or equals. It's a continuous random variable. It doesn't matter. The probability of being at any of these individual points is 0, so it doesn't really matter. I can be sloppy there. In fact, you can, for a continuous distribution, you can change any countable number of points to whatever value you want for the PDF. It's not going to change the answer because the integral over a countable set is 0. They just won't add up. They're not dense enough to matter. And so in this case, I mean, you could add, say, less than or greater than. Doesn't really matter because the probability of being at that point is 0. So it's probabilists are kind of, in statisticians, they're kind of very sloppy on those edge cases generally. So you'll see that quite a bit. Okay, other facts about the continuous uniform distribution. Of course, we could ask what its expectation is. So what's the expected value? Well, we have a formula for it, right? In this case, it's the integral. Well, it's always the integral fx dx over the whole line. In this case, we only have to worry about between a and b, because otherwise fx is 0. Between a and b, fx is 1 over b minus a, and we get an x there and a dx. We can factor out b minus a. So at this point, right, not a probability problem, it's just a calc 1 problem. Factor out my b minus a. This is, what are we left with? X squared over 2, evaluating between a and b. And that gives me b squared minus a squared over b minus a. Of course, I can factor b squared minus a squared as a plus b times a minus b over b minus a. A plus b times b minus a, right? Equivalent, right? Doesn't matter. Those cancel is the point. And I forgot my 2, right? There's a 2 down here. And so my expected value is a plus b over 2. That looks really familiar. That's exactly the same as discrete uniform. And it's, you know, a reasonable answer for the same reasons, right? If my density is uniform between a and b, where would I put my fulcrum to balance things? Of course, I would put my balancing point at the arithmetic mean, the mean of them, a plus b over 2, the midpoint. Right? And that makes sense. And indeed, that is the expected value. So it's somewhat interpretable. And we could ask for the variance. And using our shortcut formula, of course, the way we want to calculate the variance is, let's get the second moment here. All right? Is it the second moment? Let's do this quickly. Is the integral a to b. And now instead of x f of x, it's x squared. F of x is, of course, b minus a dx. And at this point, you've written it down. Now it's just a Calc 1 problem, right? Factor out b minus a. This is x cubed, a to b. So you get b cubed minus a cubed over b minus a. Does that seem right? And although you probably don't remember the formula for cubes, you can write a cube, a difference of cubes as b cubed minus a cubed as b minus a times b squared plus ba plus a squared. And the reason, whoops, we're forgetting our 3 in the basement here. The reason, obviously we want to do that, is we can get some cancellation. It's not the prettiest formula. It's b squared plus ba plus a squared over 3. But that's just the second moment, right? If we want to actually calculate my variance, I can use my shortcut formula, expected value of the square minus the square of my expected value. And so that is b squared plus ba plus a squared over 3 minus my expected value is a plus b over 2. Square that. And I'm not going to bore you with the algebra. Do some algebra. You can derive that this is b minus a squared over 12. Now that might seem familiar. Stare at it for a second. B minus a squared over 12. If we go back to our discrete uniform, the variance was b minus a plus 1 squared minus 1 over 12. If I ignore that plus and minus, it's very similar to the discrete uniform distribution. Not quite exactly the same, but it's similar. It's a squared, b minus a, something like that, squared over, and there's just 12 again. So that's nice and cute. And that's the variance of our discrete uniform. So some more nice examples. I guess the last thing you might want to look at for a distribution would be, say, the MGF. So what's the MGF for a continuous uniform distribution? Okay? So, basically we're just solving problems today. We're just doing a bunch of problems, and we'll do this next lecture also. It's just review. So you could pause this at any point. I could say, pause it now. You should be able to derive, say, for a midterm, what the MGF is of a discrete uniform. Not too bad, right? So our definition is that the MGF is the expected value of e to the tx, which is the integral of e to the tx, fx, dx, integrate over everything. Of course, fx is 0, except between a and b, so we can just look at a and b, integrate over a to b. Over a to b, fx is 1 over b minus a. We have e to the tx, dx, and again, this is a Calc 1 problem from this point on, right? Factor out b minus a, and you integrate e to the tx. That should give us t in the basement, e to the tx, evaluated from a to b, which gives us what? E to the tb minus e to the t a over t times b minus a. So that is our MGF for the continuous uniform distribution. Now, you could pause here. If you take derivatives of this, which is not bad, that's a Calc 1 problem. I could ask that on an exam. And you plug in 0, I should get, when I take the second derivative and plug in 0, I should get this second moment. And when I take the first derivative and plug in 0, I should get that, a plus b over 2. So I'll let you think about that. But that's the MGF there. Okay. So let's continue on to some other nice distributions. And the last two distributions that we're going to look at today are we're going to look at one more discrete and then one more continuous. So the discrete distribution is the Bernoulli distribution. And this is a discrete distribution. So let's say discrete. And it's actually almost even simpler than the uniform distribution. So we say x distributed as, typically Bern for Bernoulli, and it has one parameter p. And this is some probability, some number between 0 and 1. And the canonical experiment for a Bernoulli distribution is that I flip a coin with probability p of heads. And I'm going to define, so if I flip a coin, it has a probability p of coming up heads, I'm going to say x is equal to 1 if I get a heads and 0 if I get a tails. Okay? You could do this with any kind of binary experiment. Yes, no, 1 if yes, 0 if no, anything you kind of want to think about. In that case, if we do this experiment and we say x is 0 or 1, so the support of my random variable is 0 or 1, that is called a Bernoulli distribution. We could even say that then x is Bernoulli p. This be Bernoulli p. Okay, so what does the PMF of this thing look like? Well, I've told you that the support is either 0 or 1. X can either be 0 or 1, heads or tails. If I look at, so it's a discrete random variable, it takes on two possible values, 0 or 1. And if I look at my PMF, so this, of course, is my PMF here. If I look at my PMF, what are my values, right? Well, the PMF tells me the probability of being at the values, right? So what's the probability I end up at a 1? Well, I end up at a 1 if I get a heads, and the probability of heads is p. So I should end up at p for 1, and probability of tails, I end up at 0 if I get a tails, and I'll get a tails with probability 1 minus p. So it'll look something like that. They could be different heights depending on my value of p. 1 minus p might be bigger than p, right? But that's kind of the graph of my PMF. You could write this out in a couple different ways. One way you could write it out is just it's p if x is equal to 1, and it's 1 minus p if x is equal to 0. Another fancier way to write it out would be as p to the x, 1 minus p to the 1 minus x, and this is for x is equal to either 0 or 1. Notice that if x is 0, this is just 1 minus p, and if x is 1, that's p. So they're identical ways. This looks familiar, right? This is familiar. It looks like a binomial random variable. And indeed, a binomial NP with n is equal to 1 is a Bernoulli. P. So binomial is kind of a generalization of Bernoulli. So we've actually seen a lot of facts about this distribution before. This is just a really simple case where instead of doing n coin flips, I just do one coin flip. We could look at other facets. So we could look at like the CDF of this thing. That should be pretty straightforward. Fx, capital Fx versus x. And my important values in my support are 0 and 1. Of course, it's going to be 0 up until 0. At 0, it's going to jump to 1 minus p, and that until it gets to 1, and then it's going to jump to 1. So this is what my CDF is going to look like, right? We know what the jumps have to be. It's discrete, so it's going to be a step function. It has to start off at 0, it has to end up at 1. That's true of every CDF. And the jump sizes, it has to have a jump of 1 minus p here, and has to have a jump of p here, because the jump sizes in my CDF correspond to the PMF, the values of my PMF, or the probability of being at those values. And that's pretty much all you need to know if that's a valid CDF. I mean, you could think about other ways of driving it. You could write this out formally, I suppose. First of all, let's put a box around this. This is my PMF. Very, very simple PMF. And correspondingly, a pretty simple CDF. It's basically 0, 1 minus p, or 1. It's 0 if x is less than or equal. Oh, x is, be careful here. Now we have to be careful at less than or less than or equal because it's a discrete distribution. If x is less than 0, it's 0. If it's between 0 but less than 1, it's 1 minus p. And if it's bigger than or equal to 1, then it is 1. And those less than or equal are very important here because it's discrete and it has a non-zero probability of ending up at any particular value. And so we have to be very careful about the boundaries between our support. So that's the CDF, maybe not the most exciting thing. We can look at, what else have we looked at? We've looked at expected value. So let's look at expectation. And it's a pretty simple random variable, maybe even simpler than the discrete uniform, right? Expected value of a Bernoulli distribution, Bernoulli random variable, is, of course, we could write out, it's the sum of x times fx, right? But that's kind of silly. Their support is just 0, 1. So the sum over x is 0 to 1, x, and x times fx. So it's 0 times f of 0 plus 1 times f of 1. So that's just f of 1, which is p. And in fact, I could play this game and look at the expected value of x squared, which is the sum over x in 0 to 1. Now it's x squared times fx. But this is just 0 squared times f of 0 plus 1 squared times f of 1, which is still just f of 1, which is p. And indeed, you could use similar arguments to show that all of the moments, the expected value of x to any power, is just going to be p, basically by similar arguments, right? So all of the moments are p. So it's a really kind of simple distribution. What this means is that if I want to calculate the variance, I can use my shortcut formula. It's the expected value of the square minus the square of my expected value, p, and then minus p squared, or p times 1 minus p. Note, we said that for a binomial NP distribution, the expectation, let's say y has a binomial NP, then the expected value of y is NP, and the variance of y we said was NP times 1 minus p. And we also claimed that a Bernoulli is just a binomial with n is equal to 1. And so you see that is exactly true, right? If I set n is equal to 1, the variance would be p by 1 minus p, and the expectation would be p, which is exactly what we get. And similarly, we could derive the MGF for this thing. You could go and say, what's my MGF? And we've kind of already, done this, but it's like the binomial derivation, but really simple, right? So m of t, expected value of e to the tx, which is, in this case, just the sum. We only have two values in our support, over 0 and 1, e to the tx fx. So it's e to the t times 0 times f of 0 plus e to the t times 1 times f of 1. E to the t 0 is 1, f of 0 is 1 minus p, e to the t, and the p. And so that is our MGF for the Bernoulli. And that is, if we recall that for binomial and P, the MGF, was almost identical, but we had a power of n. And again, so if I set n is equal to 1, I would get this. So it seems right to me. Cool. Okay. So we've seen a lot of really simple distributions. Discrete uniform, continuous uniform. We've seen binomial now, the simpler version, Bernoulli. Both are kind of important. Bernoulli being a special case of binomial when n is equal to 1. Let's now, I think, for the remainder of this lecture, let's start looking at more interesting distributions. And one of the most interesting distributions to look at is the normal distribution. So it's kind of everyone's favorite distribution and a very important distribution. So normal, or also called the Gaussian distribution. And we had seen this previously when we started talking about PDFs. So our notation was that x is distributed n for normal, mu sigma squared. Here, mu is just some number, and sigma squared, mu being some number being the mean, or I'm going to claim that it's the mean, and we'll show that, and sigma squared being the variance, which is a positive number. And, the canonical picture of a normal distribution is this kind of bell-shaped thing. It's centered at mu, and the width of this thing, of its hump there, is proportional in some way to sigma squared. We had previously showed that, let's say, PDF, right? So it's a continuous distribution as a PDF. And we had shown that, or we had claimed that the PDF for this thing had the following form. It was 1 over 2 pi sigma squared exponential of negative 1 over 2 sigma squared x minus mu squared. And this is for any possible number x. That's the PDF. That's just a brute fact. And we had a special case. Special case being if the mean is 0 and the variance is 1. So this is called the standard normal. So we'd say x is distributed normal 0, 1, which is typically how people say it. In this case, then my PDF is much simpler. 1 over 2 pi exponential of negative 1/2 x squared. And this is for any possible x. So it's kind of a simpler case. And so what else can we, so this is kind of stuff we talked about. We haven't really said anything about the CDF. And unfortunately, there is no closed form. There's no kind of simple analytical closed form using simple functions that we can write it down in. It exists. You can numerically integrate the PDF to get it, but it just doesn't have a nice closed form that we can kind of work with. And that's just one of the brute facts of life, that you can't, nothing in terms of simple functions that you can write down. We had also made some claims. We had made some claims that we didn't show, which was that, and I think you'll believe, which is that the expected value of a normal random variable is the parameter mu, and the variance of a normal random variable is sigma squared. So the parameters for a normal random variable are exactly the mean and the variance. It is, in fact, the only distribution that is entirely characterized by the mean and the variance. And we tend to think of things in terms of means and spread around means. So that's one of the reasons that normal distributions are kind of beloved, is that they parameterize in terms of two parameters that we can very easily understand. So we hadn't actually showed this to be true. But now we should have the tools to do that. And this is going to be a case where using the MGF is actually going to be the kind of simplest way to do this. And showing that you can do it, although it's maybe not as elegant as you'd like. You could directly kind of brute force calculate, given their definitions of you calculate expected value, you calculate expected value squared, and then you can use that to get the variance. But here's a case where actually using the MGF is going to get us to a really nice result, and these values are going to be easy to derive using them. So let's instead look at the MGF, and let's derive what the MGF is. Okay, so this takes a little bit of work, but it's not too bad. So first of all, for a random variable, for any random variable, what is our MGF? Our MGF is, of course, the expected value of e to the tx, which in the continuous case is the integral e to the tx fx dx, right? And specifically, in our case, right, it's the integral over the whole real line, because this PDF is non-zero for the whole real line, e to the tx, and then let's plug in our PDF. Root 2 pi sigma squared, exponential, negative 1 over 2 sigma squared, and then we have x minus mu squared, and then there's a dx on the end of this. Okay. So, first step is I'm going to expand out x minus mu squared. X minus mu squared is x squared minus 2x mu plus mu squared. Okay? And then I'm going to combine those two exponentials. The product of exponentials, I can add together the exponents. So this is the integral. We're going to still have our constant, 1 over root 2 pi sigma squared. And now I'm going to combine these things. And I'm going to say 1 over 2 sigma squared out front. And I can move this e to the tx in there. But of course I have to multiply by negative 2 sigma squared, right? So that kind of cancels out. So I can say it's negative 2 sigma squared tx, right? So that obviously would cancel and leave me just with e to the tx. So that's allowed. And then the other part in here, I have a plus x squared minus 2x mu plus mu squared, okay? So I've expanded out this whole thing, and I want to complete the square here. So what I'm going to do with this is I'm going to do what is called completing the square. You can think of it as just an algebra trick, but first of all, we can write this thing as, this thing is, we can combine some terms, right? So there's an x squared on one end, there's a mu squared on the other end, and then there's a minus, what do we have? Minus 2x, and then there'll be a mu on one part and minus 2x times sigma squared t. All right? Okay, that's equivalent. Now this almost looks like a perfect, like a kind of squared out term, right? Because it's like x squared and mu squared. It almost, what we'd really like to do is write it kind of as some kind of square. And what we're going to do is we're going to do what we call completing the square. So I'm going to say that this thing is equal to the following, which is x minus mu plus sigma squared t squared plus mu squared minus mu plus sigma squared t squared. to actually prove something, I don't actually have to justify where that's coming from. All I have to do is show that that algebra is correct. Not great motivation, but basically we're trying to complete the square in a certain way. And so we get some nice kind of squared terms here. And in particular, we like, we're gonna really like this squared term here. In any case, you can follow the chain algebra. This simplifies, and then you can actually square this all out and cancel out the terms, and you'll get back what you originally had. Okay. That allows me to again rewrite this integral. -1 and 2 sigma squared, right? And I'm going to have some big brackets here. It is let's write it like this: x minus mu plus sigma squared t, that whole thing squared, mu squared, and then there's this minus mu plus sigma squared t squared. Okay. And so that's just an algebra trick. It's an algebra trick with a certain goal. So what I'm going to do is I'm going to split up this exponent term, right? I can always write the exponent of a sum as the product of exponents. So I'm going to do it in this way. I'm going to say this 1, 2 pi sigma squared, right? That term still stays there. And then I'm going to pull off certain terms. I'm going to have exponent of, and what do I want? Of course, I have my 1 over 2 sigma squared. And then I'm going to pull off this term, which I really like. And so I'm going to have x minus mu plus sigma squared t quantity squared, close parens, and then I can write the remainder of this at using rules of exponent, right? I'm just breaking the sum of exponent of a sum into the product of exponents. And so what do I have left? I have a mu squared minus mu plus sigma squared. Oops, that should be a plus, shouldn't it? Plus sigma squared t squared. And then there's of course, my minus 2 sigma squared there. Okay. So basically, this is all just algebra at this point. But I can recognize two things. One, doesn't depend on x. Well, ain't that handy? That can be factored out of the integral. And the second thing I'm going to notice here is that this is the PDF of a certain normal random variable. It's a PDF of a normal random variable with mean mu plus sigma squared t and variance sigma squared. And so what I'm going to do is I'm going to just take this thing and I'm going to factor it out, and then the remainder of this is going to integrate to 1. So I can just say therefore integrates to 1. And so actually all I'm going to be left with at the end of the day is the part that I factor out here. All I'm going to be left with is exp of 1, 2 sigma squared, mu squared minus mu plus sigma squared t squared. That's all I'm left with. And that doesn't involve x anymore. It involves my parameters mu sigma squared, and it involves my variable t. That, one could say, is the moment generating function. Indeed, it is. It's not typically how it's written. We could do some algebra. And so I'm going to say do some algebra. And it can be simplified quite a bit, actually. And it can be simplified into exp, exponent of ut plus sigma squared t squared over 2. that is typically how we write out the MGF of a normal. So it's, a little bit tricked, but it gets you to the form. And I wouldn't expect you to derive this, but it's good to know what this thing looks like. And you get to kind of see how this thing is actually derived, right? So what we're doing is the MGF, and basically all we did was fool around with it with some algebra until we got something that integrated out to 1, and then something that didn't depend on x. And that thing that doesn't depend on x basically factors out the integral, the rest of the integral is 1, and that's the MGF. You can simplify it down into this thing. So this ends up being the moment generating function of a normal. So this is, let's say, MGF of normal mu sigma squared random variable. So let's do some tests. We want to show that the expected value of x is mu, and the expected and the variance is sigma squared. The variance of x is sigma squared. Now, you could have brute force calculated those, but they get quite nasty. In fact, they're going to be nastier to derive than the MGF. And once we've gotten this MGF once, it's actually going to be really easy to get the moments of the normal random variable, because this thing is pretty easy to take derivatives of. And once we get those moments, we will very nicely be able to get our mean and variance. So first of all, let's say, what is dm dt? Dm dt, what do we bring down? We bring down a mu plus sigma squared t over 2. And then we're left with what's in the exponent. Ut plus sigma squared t squared over 2. If we evaluate this thing at t equals 0, what are we left with? All we're going to be left with, the exponent thing turns to 1, the sigma squared t goes to 0, and we're left with mu. And that, we know from our theorem about moments, is the mean, is the expected value. So once you have the MGF, and it took a little bit of work to get the MGF, super simple. I can get the mean like that. And so we have just shown that indeed the mean of a normal random variable is mu. And we want the variance. Let's take another derivative. Let's look at the second derivative of this thing. So you need to do product rule, but it's not too bad. What you'll get is, so the derivative of this first part is just going to be sigma squared over 2 times exponent times the second part, which is exp this thing, right? And then the product rule says we have to add on the first thing times the derivative of the second thing. But of course, that would just square that. And of course, we have to add on, whoopsies, sigma squared t squared over 2. Right? Why did I square this thing? I squared this thing because that was, you just bring down another one of them, right? Evaluate this at t is equal to 0, right? What goes away? This becomes sigma squared. Oh, this derivative is wrong, right? This should just be sigma squared t, right? I brought down a 2, so it cancels. Okay. So that should just be sigma squared t. Check my derivatives, people. Sigma squared t. Okay, so I get a sigma squared times 1, so that thing turns to 1 when t is 0, and this becomes just mu. Or mu, I'm sorry, it becomes mu squared. So it's mu squared plus sigma squared. So in this, by our theorem, that the second derivative of MGF at 0 is the second moment. So the expected value of a normal random variable squared is mu squared plus sigma squared. Hence, if I want to get my variance of this, I take, of course, the second moment minus the square, the square of my first, which is mu squared plus sigma squared minus mu squared sigma squared. So my variance is indeed sigma squared. And my mean is indeed mu. So that's really nice. That shows in a really elegant way what these MGFs can do for us. It took a bit of work to get it. Once you get it, you can really quickly derive the mean and variance. You could try solving those problems directly, and I encourage you. It's only going to be a lot harder to do than going about through the MGF. It's doable. You'll need to do integration by parts a couple times. Don't recommend. Okay. So to kind of close out the lecture with these normal random variables, there's a really useful theorem that we should mention. And the theorem is about linear functions of normal random variables. Turns out that linear functions of normal random variables are really nice. Indeed, they're also normal. So if I have any random variable and I do some arbitrary linear transformation to it, I don't necessarily stay in the same family of random variables. If I take a Bernoulli random variable and I take a linear function of it, that won't be Bernoulli generally. If I take uniform will be, but binomial, we'll see many random variables. Generally, if you linearly transform them, they won't stay in the same family. Uniforms will, and some random variables will. Normals will also, and normal random variables transform in a really, really nice way. So the theorem says that if I have some random variable x, and x is normally distributed with a mean mu and a variance sigma squared. Right now we know these parameters are indeed the mean and the variance. And if I take some linear transformation, I'd find a new random variable y, and y is ax plus b. The theorem, then the theorem says that y is also going to be normal. And I would pause for a second and say, what do you think the mean and the variance are? We kind of know. The two parameters are the mean and the variance, and we know how means and variances transform under linear transformations. So the mean of y is going to be a mu plus b, and the variance of y is going to be a squared sigma squared. Right? So the intuition is that expected value of y is going to be a times the expected value of x plus b, which is a mu plus b, and the variance of y is, of course, a squared times the variance of x by our rules about linear transformations and how variances change, which, of course, is a squared sigma squared. So that's true, but that's not enough to show that it is also normal. It could be another type of random variable that is not normal. So it's necessary that they transform that way, but it's not sufficient to show it's normal. It could be something else where it doesn't follow this. Turns out it's not. It turns out it is also going to be normal. The theorem is true. And the proof, again, because we have this MGF now, this super powerful object to have, we can prove it really quickly with the MGF. So let's do that. It again shows how these MGFs, which seem a bit obscure, and how powerful they are in certain problems. We've seen that kind of once already as normal. Our theorem says that the moment generating function of y is ax plus b, is what? It's e to the tb times the moment generating function of x at at. Okay, we've seen this once already in this lecture. And we know what the moment generating function of x is. X is a normal mu sigma squared. And so let's say as an aside, right, the moment generating function of x at t is exponent of mu plus sigma squared t squared over 2. Right? I'm sorry, mu t plus sigma squared t squared over 2. Right? That was our MGF. And so if I plug in instead of x, I plug in, or sorry, if I plug in instead of t, I plug in at, we get exponent of, or we can be consistent with the notion, e to the mu at plus sigma squared a squared t squared over 2. And now we can just play around with combining exponents, right? I can combine my exponents, and I can say this is e to the a mu plus b times t plus a squared sigma squared, let's group that, t squared over 2. And now what we do is we notice that this is the MGF of a normal random variable, and it's the MGF of a normal random variable with mean a mu plus b and variance a squared sigma squared. And so that actually does prove the fact to be true. Because if I know the MGF, I know exactly everything about the random variable. So if I know the MGF and the MGF is normal, is the MGF a normal random variable, then the random variable is normal. All right. So MGF tell me everything. All right, just to say that again, if the MGF follows the form of a normal random variable, then the random variable is normal. So it's not enough to say, the mean, the variance would follow that. We have to also prove that the distribution of the probability is normal. And one way to show it is that the resulting MGF under the transformation takes the form of a normal MGF with certain parameters, and therefore the random variable is normal. So that's an incredibly powerful theorem, because it says that not only do the mean and variance transform nicely and simply, but the random variable stays in the family, that is, under linear transformation, normal or still normal. So we've seen some distributions today. We saw uniform, discrete, and continuous. We saw Bernoulli and its relation to binomial. And then we see normal. We see normal shows us really kind of about the power of the MGF. And then we have this theorem about linearly transforming normal random variables and how it works out real nice. We'll stop there. Next time we're going to come back and talk about more random variables and show more examples of how to calculate these things.